Hello to everyone, and today I'll be discussing the vibrational Raman spectra about this Raman activity of the vibration. And if you remember, then when we discussed the classical theory of the Raman spectra, for the classical theory for the vibrational one, then the vibration should also alter the mic polarizability. It means that if you remember, we wrote this alpha is equal to alpha naught of vibration plus alpha 1 of vibration sine 2 pi of nu vibrational of t. So if this quantity is non-zero, then only it means that these vibrations are altering your polarizability. Now, if molecule has little or no symmetry, it is straightforward to decide whether these vibrational modes are the Raman active or inactive. And if we are going in a much detail, usually to say that the all modes of the vibrations are the Raman active. But once you are going in a much detailer, that if you have a very sometimes it's very difficult to have only the considering the symmetry of the molecules, whether these are the symmetric molecules or symmetric molecules vibration are altering your vibration Raman polarizability or not. Now, without detailed consideration whether or not polarity changing during the vibration. So the first example we have in last class we have discussed about the triatomic molecule. For a triatomic molecule, the symmetric top molecule, that is the water molecule H2O. So simple asymmetric top molecule H2O, whose polarity ellipse we have already discussed. Now in detail, so we are illustrating here this fundamental modes of the vibrations. Fundamental mode of the vibrations are number A for the H2O, that is the V1 symmetric stretching. So in the first one, then this is the center one. I am representing that the equilibrium position, that is OH of H, right? So we have for this we have a ellipse and this polarity this one. Now these are symmetrically vibrating, means that a hydrogen atom going stretching out or shrinking in. So now in the left side, if I am representing that this H goes here and H goes here, means that these atoms are moving this fashion. And here, if I have this H and this H, means they are moving towards the O atom. So now in this case, what will happen if this bond is stressing? It means that these electrons are firmly attached. If they are firmly attached, this bond will be more polarizable. It will be producing the more polarity. If it is producing the more polarity, it means that the size of the ellipse is reducing. Because if you remember that the polarity is proportional to 1 upon under root of alpha I at that particular point. So now the shape of, because the symmetric one, the shape of the ellipse is remaining the same, but the size is reducing. So I will be having that this one. On the other hand, now once these hydrogen atoms are shrinking, it means that the bond, these electrons will be attached more strongly. It means that the polarity will be reducing. So then you have a little bigger of ellipse. Now in the extreme left is stretching out, then the extreme right you are stretching in. Then, so now when the bond is stressed, then there are less, these electrons are firmly held by the nuclei, and so the bond becomes more polarizable. The polarity of ellipse S2O may be expected to decrease in the size, and on the other hand, the size of this of the polarity ellipse is expected to increase in the size. In a B, in a condition this B, that is the number 2, that is the V2 mode, bending mode. Again the center one remaining the same, that is the equilibrium position H and this H, and you have this same size. Now over here, then this bending over here. Now this H is here, you have this O and this H and this H. Now in this case, what happening that these hydrogen atoms are bending like this. If you have a particular angle, this is a O now, these hydrogen atoms are moving like this, moving like this. If these are the moving like this, it means that almost they are forming a linear axis. They're all this is linear diatomic. This is a triatomic molecule. If the linear this triatomic molecule, this bending, obviously the shape won't be remaining the same. The shape and the size of the my polarity ellipse will be changing. So here I'll be getting that this kind of the ellipsoid. On the other hand, in this case, this hydrogen atoms are moving in this direction. Almost this H atom are overlapping to the vertical axis. In the vertical axis, then your shape of the ellipse is changing, or this. So now the ellipsoid in this fashion. Now, what's happening in this case? The ellipsoid which changes the most, ellipse is changing the most. The vibration is very large, amplitude at the extreme on the left. The molecule approaches the linear configuration with the horizontal axis, while at the other extreme on the right, it approximates the diatomic molecule as H and S atom are overlapping in a vertical axis. Now finally C mode, that is the C mode, that is the V3, that is asymmetric stressing. Again this center one is remain this my equilibrium position. Then what will happen that, so all be careful, and these all ellipses are the same size, same size. Now what happening that in this one H, these are the two H atoms. One is coming towards the my center atom O, another is moving away from this one. So what will happen in this case? In this case, now in the extreme left, suppose H is coming forward, shrinking, and this H is moving ahead. This H. What will happen that this bond is no longer much polarizable because these are very strongly attached electrons. In this bond, you have these electrons are firmly attached. It means that what will happen? We are expecting the shape and the size of the ellipse is remaining the same. However, the orientation of this my minor axis and major axis will be changing. So this is my major axis. This is the case. Now here you have O. This is my H and this is the O. Then you have ellipses somehow in this fashion. All ellipses in this case are having the same size, but the orientation is changing. So all three vibrational modes in my water molecule changing at least one aspect to the polarity ellipse. So they are changing the polarity ellipse. So all three modes are my Raman active. Now considering another example, that is a linear triatomic molecule, that is the CO2. Now once I am going for the CO2, again this is C, O and O. Center part is again I am representing the equilibrium position. Right? So illustrate the extreme cases, that is the extreme stressing or the bending or the equilibrium position. With respect to the equilibrium position, we will be finding out these modes. So whether we'll see that whether this all modes of this CO, this linear triatomic molecule are the Raman active or not. We'll see that. If you have a symmetric one, the symmetric one, it seems that they must be having the some polarity changes. In the same way, if I'm looking at what we have done in for the S2 and the CO2 as well, we see that this asymmetric and the stretching, symmetric stretching and asymmetric stretching and the bending. So the bending mode and the asymmetric modes of stretching, we'll see that whether these are the Raman active or not. So we need to go much detail or to be carefully to examine this configuration. So the first example, the first case is that again you have ellipse, polarity ellipse in this fashion. Now if O and this O, extreme left, they are moving away from this center molecule, that is the C, then obviously again this bond is stretching. It means that you have the case where the polarity is increasing, means the size of the ellipse is reducing. So you have in this fashion. Now here you have C, O and O. What will happen that now the polarity is reducing, means that the ellipse size of the ellipse, shape of the ellipse remaining the same, size of the ellipse is increasing. So I will have some kind of this one. And more interestingly, to define, now if this bond is stressing, and if I'm defining that is some parameter, this xi is I'm defining this xi. Suppose I have this minus of xi and plus of xi. If bond is stressing, I have some increase in the xi, that is some parameter I'm defining. So this is my alpha naught, some constant quantity, that's the induced one due to the incident light. However, whether the vibrational is adding on this polarity or not, that is alpha 1 of V. So bond stressing, then you have this stretching in this fashion. Suppose at this xi is equal to 0, xi is equal to 0, this is xi is equal to 0. Now, if bond is stressing, you have some increment in this xi. And if bond is reducing, then some the xi is constant. The value of xi is decreasing. So you have this one. Now, this is the first case. So the second case is a symmetric stretching mode. So, second mode is bending mode. B is V2 bending mode. So again, this center one is again this my equilibrium position. These all are same sign, and be careful. Right? Now, now this is a hydrogen, this is my center at here. I have this my carbon atom, and this side and this side are my oxygen atoms. So this is the bending is happening in this upward and the downwards. So for the upward, I am defining this parameter xi is a positive, and this is my negative one. So now in both the cases, if you look at, so bonding, and so in this case, if I have this C, this is O, and this is my O. So what will happen? So in the case of this this V2 motion, so here finally what happening that this alpha is you are increasing. This alpha is increasing or decreasing. That is the change is taking place at once this xi bond is stretching out or is stretching in. There is a change in this xi. So now in this case of this B case, once that V2 is bending motion, it can count a downwards displacement of the oxygen atom at a negative, and the negative xi, and upward displacement as a positive. So upward Upward, I'm representing this positive one, and the downwards, I'm negative one. So, if I will plot for this one, the shape of this ellipse will be changing. Then, if almost circular one, so this C is here, and this O is here, and the O is here. Again, this one. So what I'm saying that this plus of xi and my minus of xi and the plus of xi, this is my alpha naught. Upwards, if the bend is going upwards, then I have change in the xi. Again, it's downwards, then it is changing. Means what? It means that the bending, we can count that the downwards displacement of the oxygen atoms as a negative xi and the upward displacement as a positive. Although it is not clear from the diagram whether the motion causes an increase or the decrease in the polarity. Actually, it is an increase. In a plane that the change in exactly the same for the both the positive and the negative xi. If you look at the change, here the change is symmetric one as compared to this one. So here is a completely asymmetric one. The change in the bond, if these are motion is upwards and downwards, there is no change at all. So if you look at, there is total change in this my xi. So I have at this point somehow this kind of. Both the cases you have a changing in the positive direction of this xi. And the last one, once I have the C part V3 of a asymmetric stressing. Now this is C again, the center will remain this my equilibrium position, then you have this ellipse. Now what happening that, now this one is coming in and another is going out. So this is asymmetric mode. So again, we're expecting that the shape of my ellipse is remaining the same, but size is changing. So here, if this molecule is going out, means this is going out, and this remains this O, then you have this ellipse. And if this is going out and this is remaining at the equilibrium, then you have again this mode. So again, I'm representing this plus minus xi and a plus xi, and this alpha naught, this is alpha naught at this point. At xi is equal to 0, there is no change at all, where this alpha naught is induced dipole moment from the external field. However, if there is a change in the polarity, I'm defining the parameter xi, then in this case, what will happen in that? So in the case of C, here the polarity decreases equally for the positive and the negative. So in this case, my polarity is increasing for the upward motion or the downward motion equally. But here, what happening that here polarity is decreasing with respect to the xi in a negative direction. So I'll be getting somehow this condition. So overall, if you look at now this d xi, so at this point d alpha divided by d xi, that is tangent at this one, is not equal to 0. However, once I will plot a tangent at this point, this d xi of d alpha by d xi is equal to 0 and d alpha by d xi is equal to 0. Now if you look at, in the previous case, there is a significant change of these modes in my polarity for the water molecule. So all the three modes are active for the Raman. However, in this case, this non-zero tangent, this non-zero slope, that is slope, at xi is equal to 0, I am plotting slope. For this, I have this non-zero. However, for this one and these two modes are this 0. So the slope that d alpha by d xi is not equal to 0, at z is equal to 0. Thus, all small displacement of the motion produces a change in the polarity at the Raman active. So, it is producing the change in the polarity and therefore the Raman active. Now, in these two cases, if there is a small change in these two modes, V2 bending mode and the symmetric stretching mode, the slope is 0 at z is equal to 0. So in these two modes are the Raman inactive for a small displacement, and that is why these are the Raman inactive. So we could follow the same reasoning that what the three vibrating modes of the molecule, hydrogen water molecule, discuss. In each case, we have been discovered that this alpha versus and xi curve has the general slope or its mirror image. In other words, each d alpha by d xi is not equal to 0 in the case of the, if you look at for the water molecule. And that is why all the three modes are the Raman active. In the general, however, the slopes of the three curves were different at xi is equal to 0. That is, the d alpha by d xi would have different values in these two modes, this linear molecule, but only allowed for d alpha by d xi mode is active for the Raman. So, the polarity curve has large slope at xi is equal to 0, the Raman line will be strong. So what will happen if d alpha, if d is slope is large, then I will have a sharp line. If the slope is small, it will be weaker. And it is 0, not allowed at. If it is a 0, it means it is not allowed. It means this is 0, slope is 0, that is not allowed. So we are forming a general rule now, we are defining a general rule now. So in this case, symmetric vibration gives rise to intense Raman lines, because symmetric modes gives the intense Raman lines. Non-symmetric ones are usually weak and sometimes not unobservable. Means if you have a symmetric vibrational modes, you have a intense lines, or the non-symmetric one are usually the weak and the sometimes unobservable. So means that if the symmetric stretching in the case of the water molecule, you are getting the sharp line. For another two modes, you have for the bending and the asymmetric stretching, you have a weaker lines. On the other hand, in a carbon dioxide, CO2, for the symmetric mode, you have a strong line, but the two modes are the unobservable, means Raman inactive. So, in particular, bending motion usually yields only a very weak Raman. So, the bending lines, for example, V2 motion of the S2. Although these modes are the Raman active and has not been observed, and even for the V3, that is the asymmetric stretching, this d alpha and the d xi is very small, and in that case we have very small, very weak lines of the Raman. Okay, now let me discuss rule of mutual exclusion. Rule of mutual exclusion. So further to extremely important general rule has been established, whose operation may be exemplified by carbon dioxide, as one of the symmetric stretching mode is providing with Raman active and the two rest modes are the inactive. So we can summarize that the Raman and infrared activities of the fundamental vibration of the molecule. I am tabling these modes. So mode of vibration, for example, the CO2, V1, V2 and V3. This is a symmetric stretch, bending or asymmetric stretching. So we have Raman and infrared. So this is a active, this is my inactive. This is inactive and inactive. This is active and this is active. So we see that for this molecule, no vibration is simultaneously active in both the Raman and the infrared. Now, at least for it, both are not simultaneously active in both the Raman and infrared. So the corresponding general rule is, now we are defining rule of mutual exclusion. So if a molecule has a center of symmetry, then Raman active vibration are infrared inactive, and vice versa. I am repeating it now. If a molecule has a center of symmetry, then the Raman active vibrations are infrared inactive, and vice versa. If there is no center of symmetry, then some, but not necessarily all, vibrations may be both Raman and infrared active, as we have discussed in the case of the water molecule. So now we convert this rule, this exclusion rule, also to that the observer of the Raman and the infrared spectra showing no common lines implies that the molecule has a center symmetry. But it is necessary to that, we have already seen that the vibration may be Raman active, but to be observed. However, if some vibrations are observed to give coincidence Raman and the infrared absorption, it is certain that the molecule has no center of symmetry. There is no center of symmetry, but it is providing you infrared and the IR as well. So this extremely valuable structure information to obtainable by the comparison of the Raman and the infrared spectra of a molecule. So if center of symmetry, then what you have, you do not have both the lines, means infrared active lines and the Raman lines are not present. However, once you may have a symmetry in a molecule, then you may have both the one. So that is why it is very important, what I said, that in the conjuncture of this Raman spectroscopy and the infrared spectroscopy, the structural information can be found of the molecule. So in detail, after the vibrational spectra, we will be discussing a little bit about this, finding the structure of the molecule with the help of the Raman spectra we will be discussing. So today all about this vibrational mode of these molecules I have discussed, and tomorrow I will be discussing the vibrational Raman spectra and this rotational fine structure. Rotational fine structure means this rotational fine structure, it means you have the vibrational mode along with your rotational modes. That is the fine structure what we did for the vibrational rotator. So that will be tomorrow I will be discussing. Thank you for